Morning is Francis Poulin, who is a professor in the Department of Applied Mathematics here at the University of Waterloo. Francis, I think, represents a lot of what we're trying to do here, which is bringing together mathematicians and mathematics with the areas of application that are of very important to all of us right now. Francis takes his work in mathematics in stochastic differential equations and computational mathematics and applies it in the areas of biological and geophysical fluid mechanics. And he's going to tell us today about complexity on Earth.
Okay, thank you. Thank you for the introduction, and thank you everyone for coming to my talk and to this very fascinating workshop. It's a pleasure to be here to speak to such a diverse range of people from different areas, and I'm hoping to learn from you throughout the week. So last week I gave a conference talk which was 8 minutes long. Now I have 1 hour and 20 minutes, which is the other extreme. I feel much more relaxed about that. I do want to consider this to be more like a conversation. I am the guide. I will be showing you some pictures. I will be saying some things, but I want you to feel free to ask questions, to share your thoughts. I'm not really an expert on most of the things I'm going to be talking about. I certainly know some things, but if you have other insights you want to share, by all means, please do. If I get through half of my slides today, I'm okay with that. I don't necessarily want to force them on you. The purpose of this time is for us to discuss things together, and I'm certainly happy to encourage that in the process. Right, so before we get things started, I'd like to get to know the audience a little bit better. I don't have any breakout groups planned this time, maybe next time following Sarah's example, but who here would, just a show of hands, would consider themselves to be from a mathy area? Okay, big attendance. Who here would consider themselves from a more climate earth science area? Okay, smaller number. And who here would consider yourselves from both? Okay, so I maybe asked an unfair question, and I don't want to think of this as being silos. I do think of it as a spectrum. And there's certainly some of us here who are in the mathematics faculty, so that's very much on the mathy side, but the research we do can be very applied. I'm in applied mathematics. I think any area of mathematics I can think of has the potential for application to physics or climate in particular, in the same way that I would think that any area of climate would have some quantitative component. So I don't want to think of it as being one opposed to the other, but we are working together. And I think putting these things together can result in some very beautiful research. Okay, so my title today is Complexity on Earth, which is very vague. I thought it was a bit catchy, might get people's attention. And what I want to start showing you today is windy.com. Has anyone here seen windy.com before? Okay, so back when I was a kid and I had channels on TV, I would watch the weather and we would see pressure systems. Windy.com is a much easier way to see a bunch of different things that's going on. This is from a simulation. There are different choices you can make, but you get to see the winds that are going on. And guess what? It's complicated. You get to see that the arrows is where the winds are going. There's a lot of interesting things going on. You can focus on North America. You can move around to Europe if you want. You can see a global scale. This is, I think, a very beautiful, beautiful image. And it helps to start to show some of the complexities that do take place in the atmosphere, of which we understand some of, but some we're still working on. And so this is the first thing you get to when you go to Windy, which is great, but I always like to go to more layers because I want to find the currents in the ocean because I study the ocean. So if I can go a little bit further down, have I gone too far down? No, I haven't. So if I click on the currents, then we see what's going on in the oceans. Again, this is model data or model simulation, but we see similar stuff that's going on, but now in the oceans. And in particular, the thing that probably jumps out at you is this current here, which we call the Gulf Stream. And it does transport warm, salty water from the Gulf of Mexico northeastwards towards Europe. It does follow along the coastline for a while. It separates, it meanders, it generates these rings. It's a very important part of the climate system. And there's a lot of discussion about whether the Gulf Stream is slowing down, what impact that's going to have on our climate. An excellent question that I won't address today. It's not my area of expertise, but it's something that people are very much working on. And just to show you that the Gulf Stream is not unique in its own right, if I can manage to go to the Pacific, we can go off the coast of Japan, and we see different coastlines, we see different details, but we see something that looks kind of like the Gulf Stream. The Kuroshio is the Pacific version, or the Northern Pacific version of the Gulf Stream, and you see that is also transporting water away from the tropics towards the poles. It's also meandering, generating some rings perhaps, and it's rich and complicated. Now, I'm not going to explain what's going on here because it's not the focus of my talk, but I just want you to see some of the interesting dynamics that's going on in the ocean. And I, as an oceanographer, I do love to talk about it for one, and I also want to share with you how it's an important part of the climate system. Some might say more important than the atmosphere because of the fact that the ocean is a big heat sponge.
But you said this is synthetic.
This is from a model. Yes. Yes. So it's the model probably uses data. Well, no, if it's predicting the future, it can't use data. So the models often you do use data, but this is predicting stuff, I think, currently, if I'm reading the time correctly. And so it's a simulation based on a lot of previous knowledge and does our best prediction as to what we think is going to be happening, whether it's the currents in the ocean, currents in the atmosphere. It is a very complex system. I don't pretend to know exactly what it's doing, but it's doing the best that they can with the knowledge that we have today. Other thoughts or questions? Okay. So if I can now find my PDF again, then I will continue and I'll make it even full screen. So today I can, if time permits, talk about 4 different areas. The atmosphere, which is something that I'm not as much of an expert on, but I do value and I'm happy to talk about. The oceans, just to give you a brief overview. Then, the motivation is that in applied mathematics, my areas of research are mainly physical oceanography, ecology in the ocean, and solar physics. These are things that I find very fascinating. As a mathematician by training, my approach isn't necessarily that creative, but it's certainly something we've been doing for centuries, well, for thousands of years. In terms of, in science, what do? We first of all observe the world, because if we're trying to understand the world, we can't do that without knowing what's going on. Many of us like to describe the world using some mathematical structure, whether it's differential equations, using statistics. There's a lot of other ways you can do that, but we describe the world using a model, which must necessarily be simpler than the real world, otherwise the model is useless. Then we use some mathematical techniques to try and learn from these equations that we have with the system. And then the very important part of it is to then translate that into the real world. What does this model predict? If it predicts something that's accurate to some degree of accuracy, to some level of accuracy, then we say it's a good model, it has some value. If it says something that's very wrong, well, it's a bad model. And even good models can be improved upon. And these are things that we can do in a variety of contexts. In the spirit of observations, I guess we could go outside and look at the weather, but that wouldn't be very productive. Instead, I'll give you just some overview, general overviews of observations in the atmosphere and the oceans, just to show some of the important things that are going on. And these are things we need to better understand in order to quantitatively predict what's going to be going on in our changing climate. So the atmosphere. So this is a rather simplistic picture, but it does show you that the atmosphere can be divided and is divided into different layers. The bottom part, the troposphere, is where we live, which is around, say, the bottom 12 kilometers. And if you take a plane, or when you take a plane, it's basically going above the troposphere, what we call the tropopause, and that's where planes fly. But our lives are pretty much entirely contained within the troposphere. And so that's where we live, that's where our lives are. Above that, you can talk about the stratosphere, the mesosphere, thermosphere, exosphere. All are interesting, all are very complicated. And a simple, when you start talking about simple climate models, something that people often do is discuss the radiation coming in from the sun, which is important, why we exist on Earth, and look at how much of this radiation is absorbed, how much is reflected, looking at these balance laws, which can give us an estimation as to what temperature should be. Again, an interesting topic that one could talk about, but not something I'm going to be talking about today. I guess one theme of my talk today is to talk about complexity. And by that, I mean talking about different scales. And here, even though the atmosphere is just one entity, we can think of it as being in these different layers, which gives us, because each of these is qualitatively different in some way. They're all composed of air, but the density stratification can differ. The dynamics can differ as well. And so these are things that we do think about and do try to better understand. So not only is there variation in the vertical, well, I guess, sorry, that's my next slide. Sorry, what I should say here is that this is more or less an average of the temperature field from the South Pole on the right to the North Pole on the left. It says potential temperature. Let's think of it as being the temperature. And we are at the very bottom down here. And guess what? It's warmer in the tropics than it is in the poles. Nothing shocking here. If it said anything else, it would definitely be wrong. And we see how the mean temperature, annual mean temperature, differs with latitude on the surface of the Earth. And it doesn't include the mountains or anything, but it's just an average. As we move upwards, and I should say that the top part here is basically the top of the troposphere. And as we move upwards, the strong variation latitude seems to level out. And this height over here, the temperature seems actually uniform across the latitudes. And when you go further up, there starts to be some changes, but we do know that the temperature changes latitude, which is true on the surface of the Earth. When you go further upwards, it gets more complicated. Okay. But in addition to talking about the vertical structure, which I showed you a couple of slides before, it's also important to think about the cells, the atmospheric cells that exist in the atmosphere, because this is very important in determining the weather that we experience, and how these things change is certainly of importance. So I'm not going to tell you why these things are here, but in each hemisphere, there are 3 different cells. And in the tropics, we have what are called the Hadley cells, where because of the fact that the tropics are warmer, they're warmer, as we saw previously, there is heating, and this causes convection, which causes the warm air to rise. As it rises to a certain height, again, near the top of the troposphere, it then spreads out going poleward. And thinking about the northern hemisphere to be concrete, it goes northward for a while, and around 30 degrees north or so, it then descends, mostly because it's cooled, and so the cooler air then falls down towards the Earth, and then there's a divergence on the surface of the Earth, so you have the air coming back. And so the air comes back, which basically gives you 1 cell. Now, we know that the Earth is spinning. The rotation of the Earth induces what we could call a Coriolis pseudoforce, which means that looking at things from the surface of the Earth, things in the northern hemisphere seem to be deflected towards the right. They're not really. Everything does follow Newton's second law, which is to say that things in motion tend to be in motion, and things at a particular velocity with no forces will continue to do that. However, because the Earth is rotating, it looks like things are being deflected towards the right just because of the non-inertial frame we're looking in. And if you consider this this air which is coming back towards the tropics, if it's deflected towards the right, that's going to cause the winds to go westward. And this is what generates what's called the trade winds. from 30 degrees north to 60 degrees north, we have that the flow is actually northwards, which then deflects it towards the right still, which causes the winds to go eastward. So this is a simple way to understand the mean winds that occur in the atmosphere. And well, these are things that have been known about for hundreds of years. And back in the days when people would take boats for trading from Europe to North America, they would go down towards the tropics because they knew the winds would push them westward, and it was much better than going against the winds, and then they would go upward. So this is not new. This is very classical, but certainly something that's been very important in human society in a lot of ways. And one question you could ask is, well, why are there 6 cells? Why aren't there more? A lot of that has to do with the size of the Earth and the rate at which the Earth is spinning. If you consider Jupiter, for example, which is much larger and spins about twice as fast, we see there are actually multiple cells. Each of the bands in Jupiter can be thought of as being a cell in the same way we have on Earth, but there's multiple cells. And in actuality, I think there's around 9 in each hemisphere, which each of them kind of does the same thing. Because of the complex atmosphere in Jupiter, they have some beautiful colors. You see the great red spot over here, but it's the same basic physics, just on a different scale. Now, in addition to observing the atmosphere, which is important, people have been trying to predict the atmosphere for a very long time. And the first person that tried to make a weather prediction by hand is Richardson in 1922, so just over 100 years ago, and there were no computers, so he did it all by hand, which is an enormous feat. And I think what he did well, but the problem is the results that he had weren't really meaningful, because the model he was solving, let's say, was very complicated, and it had things like gravity waves, which we know exist in the atmosphere, but it makes the models really sensitive. And so after all this hard work, I don't think his predictions were necessarily meaningful, because he was considering something that was too complicated. So later on, Jules Charney, I think as part of his PhD thesis at MIT in 48, he came up with a simplified model, what is now referred to as a quasi-dystrophic model, which was then used for weather prediction on computers. And that was, I think, the first model that was successful. Now, that was back in the 40s. In this day and age, it's been more than 70 years. We are using much more complicated models, which we can do because we have much more complicated computers. And we are greedy in nature, because the more complicated, the more powerful computers we have, the more we want to resolve in terms of the scale, something I'll talk more about in the minutes to come. But here, I want you to just visualize this and realize this is a very simple discretization of the atmosphere, where it shows you that it's discretized in both the horizontal and in the vertical, because we can't describe all scales. If we want to describe the atmosphere as this shell over the Earth, well, we have to partition the horizontal directions and the vertical direction, and then approximate the equations on the grid, and then evolve those forward in time. There is a lot of complexity. So you can talk about the temperature, the humidity, the pressure, the velocity. There's a lot of complicated details. I'm not going to talk about that, but this is something that is done every day, many times a day, to predict the weather. And the better we can understand the physics, and the better tools we have to solve these equations, the better we should be able to predict what's going on. However, weather is a product. So it is hard, and we'll talk about this more later on, as I mentioned in the outline. So it's a hard thing to do, but it's something that we definitely need to do, because we want to understand things that's going on around us and try to adapt for it in some way, shape, or form. So it was a very brief overview of the atmosphere. As I mentioned, it's not necessarily my area of expertise, but I wanted to share some insights with you. before I talk about the oceans, are there any thoughts or questions people might want to raise? Oh, yes.
Yeah, I just had a quick question, Francis, how you were showing about the discretization and like the cells.
Yes.
And so I imagine that also part of what makes this very challenging is making sure that you have put together the code for these calculations to happen within the cells and that they have to agree with each other, right?
Yes.
With one coherent picture.
Yes.
Is that a correct way to understand what this image is conveying about how we do try to model either weather or then and then trying to think bigger to things like climate change?
Yeah, so I would say I would roughly categorize things in two areas. So there's a lot of things you can include. We can include the weather, we can include land, the ocean, sea ice. There's a lot of different components of the Earth system, but one part of it is what are the physical equations that describe the system we want to understand, which we've known the equations for over 100 years in some degree, so we kind of know what those are, but turbulence makes things very hard. But then the second question is then how do we solve them accurately? And as I'll mention later on, the models that we have nowadays, the most powerful ones, I think, go down to resolving things down to a kilometer, which is that fine? Is that not fine? It used to be 10 kilometers. So we are getting better and better, but when we resolve things, when we're able to have a finer grid, it does introduce more physics, which makes things harder. So describing things on these varying scales is a challenge. And I will talk about this a bit more later on, but I do think of it as being, well, what are the physical equations we want to solve? And then how do we solve those computationally and efficiently and accurately? And those are not easy things to do, but these are things we have to do. Yes.
Next comment, one of there is Jonathan Wyman.
Yes.
Who's also the originator of stem cell Poulin of cellular automata. So people who work in some complex methods, and so complex in cellular automata.
Yes.
That was one of Wyman's motivations for introducing cellular automata.
Oh,
whether
great.
that and self-reproduction.
Okay. Thanks for sharing. I did not know that. Other questions or thoughts?
Yeah, I many questions, but just one. I've heard that, it takes a lot of time to build up these models, and would you say there are, like 5 models globally, like literally just packets of code that people would use, or is it more like in other areas of physics where every research group kind of builds their own little tool?
Good question. There are a lot of different models. I guess different groups build different models. There is a group that actually compares, I think they have a dozen or so different models from different groups completely. And hopefully they agree, and sometimes they do, and sometimes they don't. So there isn't just one model, there are different flavors, and I think that can be a strength because, let's be honest, each model is wrong to some degree or the other. I don't mean to be overly harsh, but they do some things right, but they do some things wrong, and different models tend to have different strengths, different weaknesses, which is why sometimes when you're trying to predict the weather, instead of just running one model, what you do is the ensemble. You basically do a bunch of different runs, which is a bunch of different models, and then look at the mean behavior, and you hope that the mean is going to give you a better description than just one single model in its runs.
When you see multiple different runs, is that like in a Monte Carlo type of sense, or
Something like that, yes. So initial conditions aren't always known exactly, so having slightly different initial conditions can give you different results. And using a different model, even if exactly the same initial conditions will definitely give you a different result because the models are different. So there's a lot of variation, and I don't think we should all be using one model because there isn't one model that's right. So I think it's good that there is this diversity in the modeling world, and it is a better way for us to improve each of them and get a better idea as to what we think is actually happening. Yes.
So in your opinion, are there the current AI type models to replace this?
I don't know about that. I don't deal with AI. I know that it's a very popular thing nowadays and I'm behind the times, but I know that people are using AI in these models to some degree. But I can't comment on that because I'm just not well informed.
AI, I know, refer to learn. But in this is TFT or something, right?
Well, so turbulence is something we have to parameterize, which I'll talk about. People are using artificial intelligence to parameterize the turbulence. That's something that is going on nowadays, and some people find that it's going on. But I don't do that, and I don't know much about that, so I'm going to hold my tongue.
And just to be clear, you're not solving the equations analytically.
No, this is all being solved on very large computer clusters, so thousands of cores or something like that.
Mostly explicit method of solving Navier-Stokes, is that how you would consider in a general sense? Mostly explicit methods following Navier-Stokes.
The equations are based on Navier-Stokes in a lot of ways. Some are implicit, some are implicit, it sort of depends. Sometimes it's sort of split that some parts of the dynamic are treated explicitly, some of it, which are much faster, like these sort of gravity waves are treated implicitly. There is some variation in the different ones.
And could you give some clue for what type of new business comes in when you go to the lower?
I will talk about that, yes. We're just coming in. Good question. Okay, yes.
Just a comment, not everybody comes up in your mind about with the you mentioned the ocean is a huge heat sink, and that temperature is very important in this model.
Yes.
But another thing I've learned recently, I mean, as an outsider in the subject, is that the ocean is a huge CO2 sink, and it's absorbing 31% or something of our
Yes.
emissions.
Yes.
Does that come up in your models? Are you aware?
I don't do that myself. I know that it is a critical concern. I tend to go towards process studies, so consider very simple problems, because climate and weather is really hard. We need to do it, and I don't want to discourage anyone from doing it, but I do like to try solving simpler problems, building my understanding, building my toolkit, and then there trying to tackle harder problems. And I haven't been so brave to challenge these problems yet, but I'm certainly wanting to learn more.
You think there's some, anybody who's doing that, it's coupling, the carbon sink nature of the oceans with this kind of like.
I know that it's going on. I can't give you any references, but I'm sure there's a lot of groups doing that. I'm just not aware of them. Okay, so thank you for the discussion. I've learned some things which I wanted to, so thank you for that. I will now go on to the oceans, more of my comfort zone. So saying some things that are kind of obvious, but the oceans cover about 2/3 of the earth. Lots of food and natural resources come from the oceans. As I mentioned, the ocean is a heat sponge, and you have as much heat in the upper 3 or so meters of the ocean compared to the entire atmosphere. And there's a lot more. The ocean can go down to about 10 kilometers. So there's a lot of heat there. And it's really it'll take a long time before things can change because of how much heat is absorbed into the ocean. I won't say necessarily all of that, but on the right, and I guess one important part of understanding the oceans, as I mentioned, as part of science, is to make observations. And this is something that was recently published in ECHO by NASA, where they're showing the results they're showing results of observations of the Gulf Stream due to satellites that were, say, built a while ago, I forget which ones. And in December of last year, there was this SWAT group that got started with much better satellites, and now we can do this well. So before, old technology, as of a few months ago, we can see the ocean much better than we ever could, which is wonderful. Now we have a lot more data. And we can resolve things down to smaller scales, which I will talk a bit more about later on, I promise. But observing the oceans, whether it's through satellites, whether it's through gliders, whether it's through boats, this all gives us a lot of information. As much information as we have, it's never enough. Because the oceans, as I mentioned, are about 10 kilometers deep. Even if we know the free surface really, really well, what's going on beneath? And if you send a glider up and down, you get these cross sections, but there's just so much we don't know, which makes it a mystery, makes it very exciting, but also makes it very challenging to actually know what's going on in the oceans. Models give us a lot of data, but we do need to validate them in order to make sure that we believe the results. Oops, wrong key. So this is again, I think an annual average of the temperature in the ocean going from, now we have the South Pole on the left, my apologies, North Pole on the right. And well, I think might be in the Atlantic, I'm not sure, but it doesn't really matter. The important thing I want you to see, which again is not too surprising, is that in the center, we have that the ocean is warmer. So in the tropics, tropical waters are warmer than polar waters. This is no shock and we do know that there is this gradient in temperature on the free surface. This shows us a bit more what's happening beneath. And we do see that there are these bowl type shapes, which aren't necessarily very smooth, but we do see that these lines of constant temperature actually meet up with something at the tropics, but below the free surface. And one thing I want you to appreciate about this is that obviously the lines of constant temperature aren't flat. They're clearly very curved, bowl shaped. Why do I think this is interesting? Well, the lines of constant temperature are associated with the density. So this means that the lines of constant density are also bowl shaped, which means that there's a lot of potential energy. Because if you have this in your sink, somehow you were able to get this in your sink initially and you let it go, what would happen is, well, the water naturally wants to have the denser water at the bottom, lighter water at the top. It's basically going to fall. It'll slosh for a while. Given enough time, you'll get a state where the lightest water is at the top, denser water is at the bottom, and that is the end state. But here we have that, and this is close to this is the mean state. We do have that the density surfaces are tilted, which means there's a lot of potential energy. How can this happen? Well, associated with these density changes are vertical changes in velocity. So there's actually a vertical shear, which is just the right amount to basically balance this state. But the existence of this state allows for the release of potential energy through a mechanism called baroclinic instability, which is very important in the oceans and in the atmosphere as well. Something I do study in my research, but I don't want to go in that in too much detail because it's, well, even though I love it, I don't want to focus on that because I don't think it's necessarily appropriate today, maybe another time. So another part of the oceans that I want you to see is that, well, the oceans are clearly three-dimensional. Horizontal, vertical is all there. But we, as theorists, we do try to understand the world by simplifying things. In particular, we can sometimes decompose the ocean, if you will, into two different parts. One is the horizontal aspect, so the horizontal motion, and one is the vertical motion. And the vertical motion involves, well, how does the water go from the top to the bottom and vice versa? And what I'm showing you here is a very simple, idealized view of the conveyor belt in the ocean, where the blue water is, where the blue color corresponds to deep water, the light gray is it, or light blue is surface water. And there is, well, the water clearly travels throughout the oceans. That's not too surprising. What may be surprising is only a few regions where we have sinking or rising. In particular, in the North Atlantic near Greenland is where we have water sinking from the surface of the ocean down to depth. Well, why does water sink? Water sinks because it's dense. Why do we have dense water here? Well, it's cold, and cold makes water denser. And so that is what contributes to it. One major concern nowadays is the fact that there's a lot of melting of sea ice. Sea ice tends to be fresher. That is going to, well, people speculate that that is impeding the amount of sinking that happens. Could there be enough melting of sea ice so that this stops? Maybe, don't know. Not saying it is, not saying it isn't, but the Gulf Stream transports water northeastwards, which contributes to part of this. But then there's a whole issue of how does this sink and how much of it is sinking? There's only a couple of regions where you have strong upwelling is maybe not quite the right word, but where you have the rising of water from the bottom, which happens here in the Indian Ocean and here off the coast of Alaska. So there's only a few regions where this happens, and well, understanding those is very critical. I'll show you an animation later on very soon that tries to illustrate that quite nicely, I think. But first of all, so this is a video from YouTube. There's going to be an advertisement. My apologies. I will try to skip through it as quickly as I can. If I can, click on it. It worked before, I swear. Right, maybe it's because I'm in full screen mode. That's
You
why.
can help prevent deaths from down power lines in Ontario. Remember, always assume a down line is live and dead.
Very sorry.
Everyone at least 10 meters away. A message from the Electrical Safety Authority.
One more second. Okay, so this is again a simulation which tries to show you, I think quite nicely, the horizontal scale in the oceans, just looking at the free surface. And again, you see the Gulf Stream, which starts off down here, propagates along. And again, I want you to think about the fact that there are a lot of different scales that go on, and you can't really see it very well, but the ocean basins typically have these large scale gyres. We also have what I call these western boundary currents. There's a large vortex here that seems to be in the Gulf of Mexico. We're now zooming in to see things a little bit more closely. Hopefully no one's getting dizzy by this. But it is rather incredible seeing the different sorts of structures that do occur. And it's only showing us the velocity. There's certainly a lot more going on, but I just wanted to show you some of this. Okay, and I think I will stop with that one. And then I will hopefully find where I was before. I was in full screen. I need to leave full screen. That's a problem. Okay, and the PDF is here. Nope, that's not what I wanted. Can I find my talk? Can someone help me figure out what application I'm using? Sorry, Brenda. I will hopefully know better for next time.
Pretty sure it's still in here. It's just the other window.
Ah, okay.
Oh.
So that was one animation I wanted to show you. That this one is to illustrate the overturning circulation, which, oh, no advertisement this time. So here, this is a bit more detail showing you the conveyor belts. And this is
My name is Nadia, and my brother was Schiffer. I direct ocean physics program at NASA headquarters, transmission director.
if I could turn down the volume, there should be a volume here.
Well, I'm actually new to the ship. It is called SWAT. And today I would like to share with you why we, NASA science.
I did turn down the volume, but it has no effect. Sorry. The conveyor belt. So you see water here, which is mostly from the Gulf Stream, propagating northeastwards. This is showing you some of the water going down. It's kind of hard for me to tell exactly where it is, where you have the sinking. But yeah, the lighting is not necessarily very crisp on the screen, but it does show you the trajectories, and then we're going to be zooming out. And we will actually follow this along a little bit more. And I think, yeah, this is still some of the surface water here propagating along the coast of Greenland. And some of it goes up here. The faint water over here is water that has sunk down to the bottom. So we get to see some of the water which is propagating at depth, which is going underneath the Gulf Stream because there is a current down there. We see this water over here merges with other water that's come from up there. And now we're traveling down in the southern hemisphere going towards the Antarctic circumpolar current, but we're at depth. So it basically propagates eastward. This is the Antarctic circumpolar current near the surface. But following this water here at depth, it then goes on the eastern part of Africa, goes through the Indian Ocean, It splits up here in a couple of, well, there's a branch. Here we're off the coast of Australia. Still propagating at depth. And now we're, I guess, transitioning to this, which is surface water in the Pacific. And not doing a very good job of showing you exactly what's happening, but I just wanted you to see the sort of pathways that can occur. And it's hard to understand what's happening over the entire ocean, which is why it's a lot simpler just to focus on little aspects of it. But it's all part of the ocean system, and how this changes in time through years or decades or centuries is certainly something that we do worry about in terms of our changing climate. Okay, so I think I've shown you enough of animations for today. I will stop that. And I will hopefully be able to find, I did it again, didn't I? Explorer. Oops, yellow one. I don't use Windows. No, it's my fault. I should, clearly. Okay. Okay, so a whirlwind tour of the oceans. This is being a bit more quantitative. And the oceans are forced at planetary scales. The sun heating the earth is on a global scale. Winds from the atmosphere that we saw before blowing on the oceans on global scales. We have the tides from the moon pulling. So these are all planetary scales. And think of this, these are basically adding energy into the oceans on scales of thousands of kilometers. The dissipation that happens due to the motion of the molecules happens on the order of micrometers. So 10 to the minus 6 meters. So the forcing happens at 10 to the 6 meters. The dissipation happens at 10 to the minus 6 meters. That's 12 orders of magnitude. Lots of stuff happens in between, some of which we understand better than others. And so on planetary scales, I would say that's things on the order of 1,000 kilometers, which involves wind, solar heating, like I said, planetary waves, sometimes called Rossby waves. And this is certainly the first step to understand. Thanks to Charney's model in the 40s, we are now better positioned to understand the mesoscale motions, which are things like the Gulf Stream, the rings that occur from the Gulf Stream and things like that. And that's say hundreds of kilometers, which is still pretty large. Nowadays, we can resolve things maybe down to 1 kilometer, which the name isn't very creative, but the submesoscale. And the first two, planetary and mesoscale, are very balanced, very two-dimensional for the most part. Submesoscales is very much less balanced, much more three-dimensional and much harder. And these are things that are now going to arise when we resolve things to smaller scales, and we have to learn how to deal with that. And on the very smallest scales, we have the microscales where dissipation occurs, and there's a lot going on in between. This picture on the right tries to show you some important features. On the horizontal axis, we have the spatial scales, which goes from 1 millimeter to 10,000 kilometers. And then on the y-axis, we have time scales going from 1 second to 100 years. And on the top right, the longest spatial scales and the longest time scales, we have climate. That's what we want to understand. ENSO is somewhere up there. We have Rossby or planetary waves going down and to the left. We have fronts and eddies like the Gulf Stream I talked about. And then we go further down and we basically get down to the motion of the molecules and surface waves, and it's really hard. Yes. Pardon me? Planetary waves, good question. So we've all seen what I would call gravity waves. So if you have a kitchen sink filled with water, and if you splash your hand in it, or if you go to a pond or a lake, then waves will naturally propagate away from there because of the force of gravity. Planetary waves are waves that can be, say, hundreds or maybe thousands of kilometers large, which exist because of the fact that the Earth is spinning and it's curved. So they exist in the atmosphere, they exist in the ocean, they propagate westward, And it's not something that we have any experience with because we don't see them on our scales. We have to look at it on a planetary scale to even see them, and understanding their dynamics is complicated, but also quite fascinating. But unfortunately, I can't say you've seen it there because you can see it in a tank. That's nice. I have done tank experiments with that, but I don't have anything to show you right now, I'm afraid. Other questions or comments? Okay, so I did not show you this to scare you off, but I wanted you to see the range of scales that occur and the wealth of different things we can study, and each thing here I think could be better understood. So where do we start? Well, I'm sort of existing in this front eddy regime because that's what I like, but trying to move down to the submesoscale because it's a lot more complicated and it's more pressing now to understand it because of the fact that the general circulation models are trying to capture it. And in terms of resolving things down to a certain scale, well, this is results from a couple of different models where you're seeing the southern part of Africa. And in the figure on the bottom, this is the grid scale on the horizontal going down to 1/20th of a degree, which is much better than what it used to be, which is still considered pretty fine. But the top part is what you get when you consider 1/60th of the degree, so 1/3 the grid scale. You would think that if you just change the grid scale by a factor of 3, you'll get pretty much the same thing. At least naively, that's what I would think. It turns out science is more complicated and the physics is more complicated, and you end up generating a lot more vortical features and filaments when you resolve things down to this scale. So is it going to be that when we make the grid scale smaller and smaller, we'll always see more and more? Maybe. Is it going to converge at some point? I don't know, but I guess one of the things that I mentioned before is the fact that the oceans and the atmosphere are turbulent. And I also mentioned that we can only resolve things down to a certain scale, meaning if we go down to say 1 kilometer, we're ignoring everything smaller than that. But dissipation is smaller than that. Dissipation is essential because dissipation is what takes energy out of the system, which does occur. But we can't include things going down smaller than 1 kilometer. So what we need to do is to include some parameterizations for dissipation, which tries to describe the effect of everything smaller than 1 kilometer without actually including it in any way, shape, or form. And this is one of the hardest problems that we have in geophysics. It's also one of the most important problems because this really can determine the dynamics, and it can be quite different depending on how you do this. And there's no self-consistent way to do this. It's a lot of ad hoc, a lot of tuning, but we need to do it because if we don't do it, then we can't predict the weather tomorrow. So it's a challenge, but it's certainly something a lot of people are working on. I don't work on that myself, so I'm not going to share any great insights that I have, but I want you to realize that there is a lot of subtleties in how these work, and this is where artificial intelligence has shown to be useful. Maybe that's going to help solve the problem. I don't know. I suspect probably not, but if it helps, then that's great. Okay, so that was my longish overview, I guess, of the atmosphere and the oceans. Because we're talking about complexity, I wanted to spend a little bit of time talking about chaos, which is something that I'm sure everyone has heard of to some degree, some more so than others. I'm sure some people know more about it than I do, but I will be brave and I'll show you a picture and I'll ask you, what's that? I'm sure many people have seen this image before. A Lorentz attractor. Thank you very much. It is a Lorentz attractor, and it's something that is in any book on chaos will show this, I'm pretty sure. This is discovered by Edward Lorenz in 1963, also known as Ed Lorenz, who was a big fan of hockey. He played hockey for the team of his department, the Earth Atmospheric Planetary Science Department, EAPS. I think the team is called the Creeps. I played for them decades later, and thanks to Ed playing on it before, it was a non-checking league. I was able to play because it was non-checking, because I don't do checking. I break easily. But he loved hockey and he discovered, well, he was the first person to come up with this image here, I believe. And as part of it, he is considered the father of chaos. If you want to consider someone else, you're welcome to do that, but that's what I've heard. And I think that's probably fair to say. So what does this system do? Well, I'll talk more about this later on, but it shows the trajectory that can occur in this solution to the system of three nonlinear ordinary differential equations. I realize it's getting a bit technical. I'm sorry, I tried to make it as mathless as possible, but I have to show you some equations. And what's weird is that there are two what we call fixed points or steady solutions within each of these orbits. If you were to start off exactly at those points, you would never leave. But you're never exactly at a particular point. If you start off even just a little bit, just a hair off, then you're going to have some sort of motion, and you can end up getting orbits around one of them, say 5 times, then transitioning to orbit around the other 7 times, and then back. And the number that you orbit around one before transitioning is very difficult, if not impossible, to predict, which is connected to the problem of predicting weather. Yes.
Sorry, just to understand better, what's the X, Y, and the Z axis?
I'll show you, it's a 3-dimensional plot. So I'm not showing you the axis, I will show you better plots later on that do have axis. But this is showing you the trajectory in 3-dimensional space, from some perspective, but it's very similar to what happens in 2-dimensional space. And it could start off here, and it ends up going around in some weird trajectory around those specific points, never converging to one or the other, always continuing in this endless cycle. And whether you start out here or there, slightly off in that inertial position is going to give you a very difficult. It will be qualitatively the same, but quantitatively it will be different. Other questions or comments about this? Yes. Yes, so this is something that's apart from the atmosphere, and I'll spend some time talking about that, but this is a very simple model of the atmosphere. And if even this very simple model can have this so-called chaotic behavior, then the real atmosphere and the real ocean is even much worse. Much worse in the sense that it's really even harder to predict.
Yes, yeah, no, no. So the thing that's other than the other small things driving crazy, when somebody says, well, it's a complex system with fundamental and untraceable, and I want to bang my head against the wall.
I don't mean all systems are.
But I just wanted to say that, you know, you actually know a lot about this system out of space, and, you know, while you can't predict the exact trajectory, you can predict that energy boundary from these space will have certain patterns, and you just mentioned qualitative. So
Yes.
I just wanted to like point to that elephant in the room,
Sure.
that many people consider these systems completely unpredictable, but others who argue that.
Very good.
there are some.
Very good point, Don. Thanks for pointing that out. And I was maybe being a little bit dramatic, and we can certainly see that it's going to be in one orbit or the other. So we do know something, but trying to predict the precise location at some point in time in the future gets harder and harder. And that's something that I guess is sort of a classical thing to focus on, which I'm focusing on, but you're right, we do know more than that.
Both statements are correct in their own context.
Yes.
And I think you set up the context very well, just for the rest of the room to think about.
Agreed.
You know, there isn't a hard and fast answer to predictable or.
Yes.
Yeah.
Very good.
Please,
Thank you for sharing that. Yes.
So, we're talking about the ocean, compared to the uncertainty of information, modeling, and so on. How important is the mathematical chaos?
When studying the oceans, which I do, I don't necessarily think about chaos. I would say I think about turbulence, which is sort of chaos on steroids in a sense, because it's much harder to predict, but there are still things we know in terms of the statistics. But I don't necessarily worry about chaos per se, but I do know that there is going to be a sensitivity to the initial conditions, and that can make it hard to predict things. At the same time, we can sometimes predict things. So I don't mean to say completely, it's not, we can certainly predict some things, but the longer we try to predict in the future, the harder it is, which is why I think the rule of thumb that I've heard, I could be wrong about this, is that it's really hard to predict the weather beyond, say, 3 or 5 days with any great position, because it does get harder to find. That's just the rule of thumb that I've heard. Yes.
Could you just put a little insight when you say you run maybe this boundary of how far you can go down on the scale of what competition resources are available? How do you feel that? Is it just you need the result in a certain time and it doesn't work out in terms of how fast the competition runs, or you just don't have enough? You can only submit this number of jobs to like to grab or something like that.
So it's hard to say exactly how long it's going to be valid for, but how he discovered this, I learned recently, is that he was finding solutions to the system of equations, which he wasn't thinking about chaos at the time, just trying to understand the dynamics that can happen. And I think he saved it into a file in single precision accuracy. And when he was then reading things back to basically continue, he then learned that it's very, very different. So when you store things to 4 decimal places versus 8 decimal places, or however many he had, it can make a big difference. So I guess what I'm trying to say is that we always are going to know the initial conditions to some degree of accuracy, but even with trying to describe what's going on right now, we can measure the temperature around us right now, we can measure the currents, but we're only going to know it to so many decimal places. The more decimal places we know, the more we should be able to predict it. But at the same time, there is going to be this natural divergence, what people say in the context of chaos theory, that the solutions are always going to start to spread from each other.
That is also going back to those scales you were showing in terms of the planetary scale, and you can only go down to 20 kilometers.
Yes.
So definitely it's chaos.
That's yes. This is sort of a transition to a different topic. I guess that stuff is certainly there, but I'm going to try to hopefully explain to you how to derive this model from a physical idea of the physical process of convection in the atmosphere, just to show you where the origin, where this comes from, and to show you that there are some solutions that we can predict very easily. There are some solutions that are hard to predict depending on the parameters that appear in the problem. So it's basically the initial conditions and also the parameters as to how predictable it is. Okay. So this set of equations is fairly popular in certain circles, I guess. And I certainly think I read a book by James Glick on chaos, Making of a New Science. Was it years ago, decades ago, actually? It's been a long time, I should reread it. And it looks rather harmless from my perspective, but it is a nonlinear system of equations. There are different parameters, and I guess, what does X, Y, and Z mean? So this picture here I said is showing you the trajectory, sure, but what is the physical meaning of these different variables? And where does this equation come from? That I don't think is quite as popular as seeing this picture, which I think everyone had seen. So I just want to spend a bit of time guiding you through that. And let's see where we go. So Ed Lorenz certainly had a very deep understanding of the atmosphere and was studying convection. Convection is something that we talked about before because we saw that the Earth is being heated more in the tropics. Whenever I boil water to make pasta, I think about convection that happens in my pot. And the idea is that when you warm something, a fluid, say air or water from below, then it's going to want to rise and it creates these convection cells. This is a complicated phenomena that to describe accurately would require some version of the Navier-Stokes equations, which is three-dimensional. It is turbulent. It is very complicated. In the 60s, it wasn't necessarily feasible to be studying this computation. Today we can, but in the 60s, it was really hard. So instead, what Ed decided to do is to consider a much simplified version that arises from a model of convection. So make things as simple as possible without too simple. So what he did, to his cleverness, is he allowed for, so generally the velocity can be anything that's three-dimensional. And we're considering a two-dimensional version now just to make things simpler. He supposed, well, let's say the velocity corresponds to, you can't really see them very well, these blue arrows here. So it's a quiver plot, so it's going counterclockwise around the blue, clockwise around the red, and only consider the velocity to have this physical shape, which is an odd thing to do, but bear with me. And suppose that the x is the coefficient, so it determines of how much the velocity is. If x is equal to 0, we have no velocity. If x is equal to positive, we have some amount of velocity going in this direction. If x is negative, we have some amount of velocity going in the opposite direction. So it's one of these three things, and he supposed the velocity was only this, but with this magnitude. He supposed that the temperature denoted by theta, not so intuitive for us, but there's a reason for that. The temperature could have two different spatial structures. One looks kind of like the velocity, but shifted, and the other has a velocity which is uniform in the horizontal. Y determines how much of this temperature field you have. Z determines how much of this temperature field you have. Now I see some puzzled looks because you're probably wondering, why would you do that? There's a good reason for that, which I'm not going to be able to do justice, but the first two plots for the velocity and the first temperature field is what naturally arises in convection. Notice that this velocity here is going on in circles, and when it does that, when you see these convection cells, there's this temperature associated with it. So rather than finding the solution out of nothing, he basically said, I know this is what the velocity and temperature are going to look like. I'm going to impose that as my solution and see what happens. Okay, so that's the basic idea. And so the x determines how much of the velocity, y determines this much, how much of this part of temperature, and the z is how much of this part of the temperature. That's really what the model is doing. And that's what I say here. There are three parameters that occur. One is PR, which is called the Prandtl number, which is a ratio of the viscosity of the momentum to the diffusivity of the temperature. There's a Rayleigh number, which is really a ratio of the temperature to the diffusivity. The stronger the Rayleigh number, the stronger the temperature difference from the top to the bottom, the stronger the convection should be. And B, which only appears here, is really an aspect ratio, not so important. You can solve the system of equations to find what are called steady solutions or fixed points, and you'll find that there are three. One of them is very boring, 0, no motion, nothing happens. The other two are a little bit more interesting, and these are the fixed points at the center of the two orbits that I showed you previously. And if you start off there, either of those, you stay there, but if you're ever slightly off, something else is going to happen. And what I want to show you here are some solutions for the Lorentz model, where I'm showing you time series. So how X, Y, and Z, this is a Z tilted, not an N, my apologies, versus time. And here I'm showing you phase space of, I think, I can't see, X versus Z, right? So in this particular case, I've chosen initial conditions, X is 0, Y is 1, Z is 0, for a Rayleigh number, which is very, very small. I evolve it forward in time, and the initial condition for X basically is 0, it increases, then it decreases, decaying. Y decays exponentially, and Z increases, then decays exponentially. So it starts off here. it goes away and it comes back, and it basically tends to this solution. This is a solution to the Lorenz model, which is very predictable because you're always going to end up converging to this particular solution or perhaps the other one. Not very exciting, but is a solution that can occur. The more interesting one is this one here, where the Rayleigh number is 50 times larger. So that means that the temperature difference from the top to the bottom is 50 times larger. The dynamics is richer. You can see in the bottom in a three-dimensional plot something similar to what I showed you before, a little bit coarser, but still there. I have the fixed points as these black dots here, and you get to see the time series of X, Y, and Z. It's much harder to understand. And it seems from the first two that it's sort of oscillating around this state here, then it jumps to the bottom, jumps to the top, and it seems to be oscillating around two different states, but it's switching from one to the other, which is exactly what we see here, but showing it in a different way. Okay, so this, and well, this is definitely not periodic. It seems to be kind of periodic for some phase, but then you have this transition, and this is a different way to illustrate the chaotic system that can occur. Questions or thoughts on that? Yes.
I'm a little confused on what, so X, Y, and Z are the velocities.
So the
Of what? Cell of air?
So X is the magnitude of the velocity of the air. Yes. So if I go back to the problem that I showed you here, the convection cells, V is basically the velocity going around here in this particular motion. And X determines how strong that velocity is.
But when you say of the air, of course, the air is very different in places.
Yes.
Thinking kind of one little unit of air?
No. So we're imposing a particular spatial structure and saying the air has this spatial velocity field. It can only change in strength, but we're setting the spatial structure. It's not free to change in the spatial structure. It can just change from positive to negative or maybe zero. And in a similar way, we're saying that there are two temperature fields that can occur, two different kinds, and those are imposed. Okay, does that help answer your question? Sort of. Sorry that I failed. So right, so we saw this, and while this is illustrating an example of chaos, this is a plot that I want to show you, which is a transition from what we call a laminar flow, where this is flow of a fluid, and this is very different, but something which is very laminar is just going along these lines. Because of some random variations along the way, there starts to be some sort of meandering. There is this generation of vortices, something which we've seen in the ocean earlier today, and then it gets very, very turbulent. This is trying to illustrate the transition from the laminar flow to a turbulent flow, and how this happens depends on the parameters of the problem and the nature of the perturbation that you superimpose. So it's very rich, and this is more what happens in the ocean than the simple Lorenz model, but I thought this helped to capture the transition from something which is very simple to something which is very complex. Yes.
I'm not sure this makes sense here, but so the chaotic system that you showed with these three equations, have they been really found to be in the Earth big scale models that we showed before?
Well, it's a very simple model, and it's what I would call a truncated model. So, yeah, we'll go into a little bit of details here. So, as I will hopefully talk about it in a minute or so, functions can be decomposed into trig functions using what's called Fourier series. What Lorenz did is basically truncated the Fourier series to only allow one mode of the velocity and two modes for the temperature. So the real atmosphere has all the modes, and anything can happen within the constraints of the physical laws, but we only allow those 3 degrees of freedom, whereas in actuality, we can have any sort of velocity. It doesn't have to be those circles, it can be much more complicated, But his model does not allow.
So I mean, the question is this, like in the book, where is model well, like certain set, nonlinear set of equations, are those periodicity that you're seeing will be, let's say, I don't know, thousands of year scale or you know, that, so we can see it in observation,
So
what might happen.
I don't know what the time scales of the periods are. I think it. I don't know. I consider those details for all I forget. But there must be a natural time scale that arises for the convection problem. But that would be for convection, wouldn't necessarily be the pilot time scale because it's just focusing on convection and only convection. A very simplified version of it.
The reason I'm asking is like, you know, there's people who are skeptical about current climate change model itself might say, look, you're just all wrong because all these cycles are coming because it's all natural, there's nothing to do with us. You see, they can extrapolate all your results and say, look, this is just natural thing that's happening and you're just looking at time up there, like, you know, Sarah was showing that big archipelago stuff.
Not sure how to respond to that. I'm not claiming this model makes great predictions. I'm just trying to look at a very simple approach. And I think it would be very dangerous to extrapolate from this to the climate system. I think it would be very, very dangerous. Okay, so.
Point of time, Francis.
Yes.
We have a few minutes left, so I'm not sure how you want to wrap things up.
I will decide in 3 seconds. So the last part I wanted to talk about was chaos and power. And this is, I will go over this quickly, but I mentioned something about Fourier series, which is a way to describe functions using trig. So, for example, you can decompose this function here, which is a step function, which is discontinuous. You can approximate it as using one sine function, which is not bad, but not great, 2 sine functions, 3 sine functions, 4 sine functions, and it gets better and better the more sine functions you include. I won't go through all the details, but it turns out that you can measure what's called the power by looking at the magnitude of these coefficients in this decomposition here. So the A's tells you the power, which tells you how much of each frequency you have. When you have one sine function, you basically have the power being a delta function, just a spike, the position of which depends on what the frequency is. If you have a smooth function, you would have some sort of smooth power. And all I wanted to say is that in the case of the solution to the Lorentz problem, where it looks very periodic, the power, which is the amplitude of these trig functions, are these spikes. But when you look at a turbulent case, you see it's basically a much broader spectrum. So one way to think about turbulence is as having all the frequencies, and having this broad spectrum is a very general tendency of chaos. And I'll stop there. Thank you very much for your time. And thank you all for your questions throughout the talk.
Well, thanks once again, Francis, for showing us some of the mathematics, right, that are used to understand the various elements of the climate system. You introduced us to atmosphere, also told us a lot more about the work that you've been doing with the ocean. And so that was really helpful to sort of see that the way that mathematicians think about these issues, and also what has been gleaned from, you know, some of the fundamental mathematical research for understanding the complexity of these natural systems. So we do have a thank you.